Hello everyone and welcome to FusionEPtalks, a student-led webinar on fusion science and technology. I'm your host today. I am Daniel Medina Roque and I'm delighted to introduce today's speaker, Floriane Leblond, a PhD student at CEA Cadarache in the plasma-phasing components and material laboratory of the IRFM. Her work focuses on experimental activities and modeling of tritium permeation and inventory in the plasma-phasing components of the future demo reactor, about which she will give us an explanation today. All her work is done in the frame of a Eurofusion engineering grant. Without further delay, I will thank everyone for zooming in today, and I will now mute myself and hand it over to Floriane. Welcome everyone and enjoy the talk.
Thank you for the introduction. So my name is Floriane Leblond. Like Daniel said, I'm a PhD student at Cadarache. I'd like to start by thanking the FusionEP team for asking me to do this, and Daniel and Katya in particular for taking care of all this organization for us. So this talk is about tritium permeation and inventory in fusion reactors. That's actually almost word per word the name of the engineering grant I'm working with. So let's start with a word of short introduction and motivation on why we are interested in those topics. So like Daniel said, I am working in what is called the IRFM, which is the Research Institute for magnetic fusion in France, and especially in the plasma-phasing components lab. So I'm going to give you an overview of what plasma-phasing components are and why we are so interested in those. So I represented the tokamak with this very quick drawing of a circle. So you all know that for the magic to happen, we put some D2 and T2 in a very specific proportion, and then you light up a plasma and the magic happens. And once that is done and you've produced some power and you've solved the energy crisis, you are left with Q2, which is something that we use to write down that we no longer have a very precise mixture of D2 and T2, but something that is no longer in the right proportions for your fusion reaction to work. You are also going to get some helium and others, such as dust and other particles, and of course, a lot of neutrons. What I am focusing in my work and my whole group is this part here that we call the plasma-phasing components. And in order for you to know what challenges plasma-phasing components face, I'm going to give a few numbers about the divertor, which is the part of the tokamak that handles the largest and most critical fluxes. So divertor conditions are as follow. You are going to have heat fluxes around 10 megawatt per square meter. So if you are not familiar with what that means, that's around 10 times more than the space shuttle during its atmospheric reentry. And the space shuttle is allowed to burn some components for that. And in plasma-phasing components, we are not too happy with changing the elements very often and burning them. So you are going to need material that are going to withstand those fluxes and that are going to be actively cooled to be able to do so. You are also going to have some very high temperatures, over 1,000 degrees Celsius in a steady state, and can reach 2,500 degrees Celsius in peaks. So that's very high temperatures, and that here narrows down the material that you can use for your PFCs. Very high ions flux as well, 10 to the power of 24. Some erosion and sputtering are going to happen as well, so it's not the friendliest place to be in the divertor's shoes. And what we are going to be focusing on today is something called permeation and also retention. So by permeation, we mean all the processes that are going to take place when those tiny particles of deuterium and tritium are going to enter the metallic matrix because they are tiny enough. And after a certain amount of time, they are likely and will permeate, so travel through the the plasma facing components, and up to the outer side where you have some coolant, for instance. So it's very important when we want to have a fusion power plant to be able to predict this permeation. So the amount and the dynamics of how tritium is going to get out of the PFCs. And also the counterpart of that, which is retention, because some of those particles traveling in the bulk are going to be kept in the material and fall into something that we call traps. And we also need to account that. So let's see why we need to account all of that. So a word of tritium safety and economy. So you all have heard about tritium. It is a radioactive element. It's weakly radiotoxic, so it's way less mean than, for instance, plutonium, but still definitely radiotoxic, and you can't ignore that. And the fact that it is weakly radiotoxic is anyway counterbalanced by the fact that we need it in huge amounts for demo, because that's the frame in which I'm working. So that's going to be 55.8 kilogram per year for 1,000 megawatts of fusion power. And you can add a factor 3 on that if you want to have 1,000 megawatts of electric power. Because actually demo is going to be the first reactor to be plugged into the grid and to produce electricity. ITER is feasibility proof. It's going to have fusion reactions in it, but it's never going to put any electricity in the grid. At the contrary, demo is going to. So that's the consumption that is needed. But you know that what we consume in the fusion reaction is a tiny part of the total amount that we put in the chamber. So this causes a very large throughput and recirculation, 20 kilograms per day. And what's foreseen for something like demo would be 200 days of operation per year. So you can imagine that this is going to be actually much larger. So here you might not be too familiar of what a kilogram of tritium represents. And to be honest, I don't either. So let's get some numbers to compare that with. So I took the regulations and the safety regulations of ITER, which are in France, and that's limits put by the ASN, Autorité de Sûreté Nucléaire, Safety Nuclear Authority in France. That is the one entity that tells you if you're allowed or not to operate anything nuclear. So the ITER safety requirements are as follows. You are allowed to have trapped in the parts of the vacuum vessel, and that's the whole huge vacuum vessel of ITER, 700 grams of tritium. And you also have a very small release permits in maintenance, and not in like normal years. In maintenance years, you are allowed to get out of your whole plant 2.5 grams of tritium per year. So you can see here that tritium is going to be something that we are going to need to handle very carefully and to account for, especially because even if you forget about the safety issue, which you should not, but even if you do, you also have the issue of tritium self-sufficiency that is happening, which means that for fusion to happen, you need to have an achieved tritium breeding ratio that is over your required tritium breeding ratio. You have very intelligent, very smart people working a lot on how to achieve a good tritium breeding ratio using the neutrons of fusion reaction in order to produce tritium. So you can imagine that we cannot allow ourselves to just lose all of that efficiency into the walls if they have a tendency to suck up all the tritium. So actually, achieving a good tritium breeding ratio also has to take into account all of that, and this and tritium handling affect the entire fuel cycle. Oh yeah, and one last word, there might also be the issue of cost. So this is the current rate of tritium, so 100 kilo euro per gram. So you can see that here this release permit is actually quite costly, and that's the current rate in 2021. And this is almost all of the tritium we have on Earth right now. So now might be the time to invest in tritium. This is going to get higher. So even just on a cost point of view, you cannot allow yourself to lose your tritium, and you have to account for it very precisely. So back to permeation. Here is the anatomy of the demo first wall, which I am working on. So you have the first layer of tungsten and the second layer of urofur, and after that you're going to have a coolant. So the goal of what I'm working on is to do some experiments and also some modeling in order to be able to predict if you have a given flux of tritium, because that's what we are interested in here on this side, which is the plasma side of our plasma-facing components. I need to predict the quantity of tritium that is going to travel all through the coulants and how much is going to stay trapped in the material. So once you have that flux here established on this side, you are going to have a first step of adsorption, meaning that those particles are going to have to enter the surface and then reach the bulk. Once they are in the bulk, you are going to have the two steps of diffusion and trapping happening inside the bulk, and that's what I'm going to focus on more today. And once you reach that other end of the PFC, you have a step of desorption, and after that, you get your tritium back in here. You will also have to take into account this interface here that is obviously having an influence on what's happening. And this is just to show you that permeation is actually a very broad word that takes into account a lot of different physical phenomena. And that's actually kind of a macroscopic understanding of a lot of microscopic phenomena happening in the material. So permeation is all of this and more, diffusion and trapping in the bulk, but also surface phenomena and interface behavior. So I told you about diffusion and trapping. Once you have your particles that have entered the bulk, so the metallic matrix, they can either be considered as mobile or trapped. So mobile particles are moving in this energy diagram in those quite low energy fluxes. Wells. So which means that when you are in one of those wells, it's quite easy for a particle to get to the next one. However, you have a second category of particles. They can fall into what we call traps, which are natural defects in the materials. And you can see here with this energy diagram then that once your particles is in that energy well, it will take a lot more energy to get back to being a mobile particle. And obviously that energy is going to be brought by temperature, which means that if you have deep enough energy well here, deep enough trap, it might take almost melting your component to get your tritium back, and so that's an issue. So there are some governing equations that you don't have to worry too much about. I just put them here to show you that we need those to simulate what's happening in the PFCs. And we have in particular two kinds of parameter that you can see here. So you have something that is called diffusivity that you might already have seen in something called Fick's law. So that's what's going to be happening for the mobile particles. And for the trapping, you are going to have your traps characterized by your trapping energy here and the density of your traps. And here you can see that we have a kind of balance. So you have trapping particles that are going to be lost because you have detrapping happening, and so they get back to being mobile. And you also have some mobile particles being trapped, and that's the opposite effect. You also need to set a boundary condition for your problem to be well posed. So that's going to be our gas permeation boundary condition here with something called K here, which is solubility. So here, even if we have a super nice model with pretty equations, we are going to need some data, some experimental data to actually understand what's going on in the material. So we are going to need permeation experiments and TDS experiments. So I'm going to show you first how I do permeation experiments to measure diffusivity and solubility, and then on to TDS, which allows us to get a more detailed understanding of the trapping in a given material. Okay, so permeation. So the goal of permeation, like I told you, is to measure some experimental parameters for a given material. So I mentioned with the equations earlier, diffusivity D and solubility K. We have a third parameter called permeability phi that comes along in permeation experiments. So phi is actually quite useful if you want to do some back of the envelope calculations and know the permeation flux in steady state, if you know the upstream pressure and the thickness of your slab. So that's, again, a kind of macroscopic parameter, but very useful for short calculations. D is required for the governing equations, like I showed you. And K is going to be used wherever chemical potential appears, in particular in the Sievert's law, which is the boundary condition that I showed in the previous slide. So the permeation experiment works as follows. It consists in 2 vacuum chambers. So you have one here that is called the upstream one and another one called the downstream one. Those 2 chambers are separated by the sample of the material you want to study. That's going to be heated. And during a permeation experiment, you put a pressure of hydrogen, for instance, on the upstream side. That's going to cause an imbalance in particle here, which is going to drive the particles to get through the sample and to create a pressure rise on the downstream part. You record that pressure rise, and based on the dynamics of this pressure rise, you can infer the parameters of permeation phi, d, and k. So without further ado, I'm going to show you my experiment. So my experiment is called hydrogen permeation in tokamak relevant materials. So that's Hypertomate. As you can see here, it's a small tomato. So if we want to get closer to the diagram I showed you earlier, here is the upstream part. So that's going to be the high pressure part. Here is the downstream part. So the part where I record the pressure rise to see what happens and in the material. I have 2 units of turbo pumping in order to get a good enough vacuum on both sides of my sample, which is hidden here actually. So behind that sleeve, because all the processes I mentioned are heat activated, so you need to set the temperature of your sample precisely and control that temperature to measure those quantities. And I have a few pressure gauges on both sides to be able to record my pressures. So that's the choice. Actually, you can also do permeation experiments, and there are several permeation experiments that exist with mass spectrometers, for instance. This was done on purpose because this experiment gives good results, which I'm going to show you, but also serves as kind of a crash test to do a tritium experiment that is going to be much more complex because it needs to be done in a radioactive lab in a glove box. So this was also a way to make a permeation experiment that is as simple as you can get, even though you can see there's still a lot of pipes going on. So once I have my recording of my pressure rise, I have an analytical expression here that gives me what's happening. And here again, there's no need to freak out. What this expression here tells me is that I'm going to have a steady state part and a dynamic part. So this is an actual recording done with Hypertomate. So this is the upstream pressure. So I create a step in hydrogen here, and that creates a pressure rise on the downstream part that I record. And based on this expression here, you can find this slope here, and the time lag here, which is the time that it takes for your pressure rise to be fully established, is linked to the effective diffusivity. And the pressure rise that you have here in steady state is linked to permeability. So then we have a formula to get back to that, and we do that many times again and again to get to a good reproducibility. Okay, so just to show off, here are some results performed with Hypertomate. So this is effective diffusivity. I compared it to, so this is my work, my experimental point and the fit corresponding to it. So the experiment is performed at several temperatures to get the low versus temperature, and the comparison with results performed on Eurofer 97, low activation still for demo. Compared to other results from literature. So this is obtained for effective diffusivity here, and same thing for permeability. So this is to show that the experiment works and yields good results. So to recap, we have measured effective diffusivity and permeability. The most awake of you might have noticed that there was a tiny bit of a scam here, because I promised you that we would find diffusivity, but we found effective diffusivity. That's because when we do a permeation experiment, you still have some traps in the material that are going to affect permeation. Schematically, if you have a ton of traps, your permeation is going to be established much slower, and you're going to get a higher time lag. So what you measure actually with permeation is effective diffusivity and not pure diffusivity, because it's affected by trapping. But no need to worry, we can get back to diffusivity once we have effective diffusivity. And actually that's interesting because it gives us, it shows us that a part of the behavior of the effective diffusivity is diffusivity, and the other one in another range of temperature is called by something that is an equivalent trap. And I also promised to you that we would get K. We do not measure it directly. It's actually the ratio of phi over D. So once we are here, we are very happy with what we've done because we have all of those parameters. And that's where all the pink parameters that were in the equation, so that's good. But as I told you, we also are interested in knowing what's going on with the traps, and permeation experiments are not capable of giving us a detailed view of trapping. We only get something that is quite broad here, and we are not able to say, for instance, how many traps there are or the densities one by one. So we have an integrated understanding of permeation for this given material, but we need to resort to a different experiment if we want to know the traps, energies, and densities separately for this material. So then we move on to thermal desorption spectrometry, which is a different analysis technique. So the goal here is to measure the density of energy of each trap and not the whole of the traps all at once. So the way it's done is you take a sample that you previously loaded. In our case, we load it with gas deuterium. So we put it in a deuterium atmosphere and heat it up for the particles to get in. You have other techniques to do that. We do it first because it makes sure that we do not damage the sample. For instance, if you do plasma implantation, you are going to damage your sample. And it's also the closest we have to the permeation experiment, and we want to link all of that together. So you have your sample that contains D. You have a thermocouple that records the temperature of your sample, a heat source, and a mass spectrometer here in a vacuum enclosure. So once you start heating up your sample following a very careful ramp up, you're going to have some particles that are going to escape your sample, and the rate at which they escape is going to be linked to the temperature, and you record all of that. And you get something that we call the TDS spectra. So it gives you, in function of the temperature of the sample, the desorption rate. And here is an actual Eurofer 97 TDS. So here you can see that we have a temperature from room temperature to above 800 Kelvin. And this is the normalized desorption rate. So what we see here is that we have a first desorption peak that corresponds actually to a first trap. So this trap is going to be rather low energy and high density. And then when you move on to higher temperature, you get a higher energy trap here, but probably with a lower density. So now we are quite happy because we are actually capable to say, okay, we have two different traps and they are behaving differently. However, we would like, for the sake of modeling, to get to the energies and densities of each of the traps. So you have mathematical formulae to perform the TDS several times using, for instance, a different heating rate, and then evaluate your the actual energies and densities. We resort to something that is slightly more complex, but also it also has its advantages. So we have in the team someone called Rémi Delaporte-Mathurin, and he wrote a finite element code that is called FESTIM. Actually, he presented it in a similar FusionEP talk not so long ago. So his finite element code is able to fully replicate the steps of TDS, so the loading, the phase where you just pump, and the phase where you heat up the sample and you see what's going out of it. And using this very modular code, we are able to do parametric optimization. So we run the code using, for instance, the energies and densities as free parameters, and we put that in an optimization algorithm in order to get as close as possible to the experimental one. So that's how we get the energies and traps. So we can start here with a first guess saying that we have two traps here. So here is what FESTIM yields with two traps. So you can see here that we replicate quite well trap 1 and trap 2, but we show doing that here you have some kind of shouldering that happens, and that is actually not covered by the two-trap model. So based on that, we say, hey, there might be something going on around here. So we can add a third trap. And doing the fit with a third trap, we have here a better understanding, and we even witness a third trap that we did not really see with the bare eye when we first did the analysis. So that's how we do it, and the promise is filled. Using FESTIM and the parametric fit, we yield energies and densities for each trap, so we are able to complete our equations, and we have everything we need. So if we have everything we need, what do we do now? And why am I presenting this to you if like this field is solved and there is nothing left to do? Actually, don't you worry, there is a lot for you to do. So it seemed that we have all the parameters for the governing equations, but that was only for one isotope, which is hydrogen. And actually, hydrogen is not going to be used in fusion. We are going to have deuterium and tritium. So for deuterium, we have laws because it's basically hydrogen but heavier. So we have a mass ratio, and we say that everything is behaving kind of the same with the mass ratio. However, tritium is not exactly just heavier than deuterium. You also have well, radiation effects happening, so you can't just put a coefficient on it and hope for the best. So you need to perform other experiments using tritium. You also have, we also have done that just in the bulk, but I try to tell you that it's not just about the bulk, it's also about the surface and the interfaces, and for a given material. So we might also have to do that for a different material, and especially when we saw that PFCs are actually multi-layered. So here we rinse and repeat and do all of this again on with other isotopes and with other materials. And even with that, we are not done. So here is what I showed you. And here again, there was a slight bit of a white lie because I simplified it for the sake of simplicity. So we did not mention at all the surface effects, but they are very important. So that needs to be investigated, especially the presence of oxide is going to compete with permeation and change the whole behavior. We also have to take care of interfaces because obviously there is one here, but there's actually another one here. And depending on what you have on the other side and which coolant is picked, the interface is going to be different. Also, there was also a white lie here because the interface for demo PFC is not going to be a short and sweet interface with just tungsten and Eurofer. Is going to be something with interfaces and a functionally graded material, meaning that the first layer here is going to be 80% tungsten and 20% Eurofer, and so on until you reach 100% Eurofer. So here you are going to have a lot going on. I also did not mention other species, in particular helium. In particular, helium is supposed to and expected to be in the material, just because if you have tritium in there after some time, not so long because it's only 12.3 years, the half-life of tritium, you're going to have some helium. So you can imagine getting helium bubbles in the material, and you want to take that into account as well. And a lot of other stuff, including, for instance, the neutrons influence, because the very high energy neutrons that we are going to have in fusion reactors are expected to create what we call extrinsic traps, which are going to have probably much higher energies than the traps we saw, and then create much more retention. So as you can see, there is still a lot to do in that field, both in the experimental part and in modeling. So if this did not scare you too much, we would be happy to take any applications. And this was just to tell you all there is to do in PFCs, even if you just take care of the particle part. Thank you so much for your attention.
Thank you very much, Floriane, for a very interesting and well-organized talk. Now we will start with the question and answers part of the talk. We have one question for here.
So I saw on your figures that the temperature when you model or you measure everything is around 500, 800 kelvins or something like that. Is it realistic in case of demo? Because it seems to be a bit low for me.
Okay, good question. So first, Eurofer is not the actual like armor material, so that's not the one that is going to take the higher fluxes. So what we do is first, in permeation experiments, what we know is diffusivity. So like I said, diffusivity is actually effective diffusivity that we measure. And if you look at that, when you plot it in an Arrhenius law, you get behavior at higher temperatures. So actually, this could be schematically put as two different slopes. You have one at very high temperatures and one at lower temperatures. So we choose that temperature range for permeation because it allows us to span both the trapping effects that are taking place at lower temperatures and the just pure diffusivity effects happening at higher temperatures. So for permeation, with that range, we span the temperature, and then there is nothing there is nothing more happening at higher temperature, so we can infer the diffusivity. Also for demo, what's foreseen is temperature that are not ranging much higher than that for the Eurofer parts. This is actually not the divertor. This is the first tool, so it's not handling fluxes that are as intense as the one I mentioned for the divertor. As for TDS, actually, if you are familiar with TDSs, you might have noticed that we stop at rather low temperature. Also here, you can see that the desorption rate is not 0, meaning that we still have some particles in the sample that we did not desorb. So it's not because we are lazy and we stopped too early. It's because we wanted to be able to fully model what's happening in here. And after that temperature, you have a phase change happening in Eurofer. So we were not really able to model what would be happening after that and what the desorption would mean. So we stopped there. But actually, yeah, the temperature foreseen for the PFCs of demo in the Eurofer part are not that high.
We have another hand raised.
Hello. Andrei Ovcharov, ITER organization, Tritium plant system engineer. Okay, you described, I would say, the general classic approach to determination of diffusivity, solubility, and the trapping parameters. But again, I'm not a specialist, but from my rather superficial understanding of the real situation for fusion machines, the most important parameter that is not really known to any meaningful, I would say, level of precision is the recombination rate on the surface. Because all these parameters like diffusivity, recombination rate to water, basically, I would say, is not really influencing anything in terms of tritium permeation to coolant, but the recombination on the plasma facing surface is actually known, at least for steel, with something like 6 orders of magnitudes difference between different experiments, and everybody repeats the same. It strongly depends on the surface conditions, how clean is the surface. There are theoretical estimations by Baskis, I don't know, a more modern kind of variation by Ogorodnikova, but all those produce results that are absolutely irreproducibly experimentally, at least for steels, as far as I know. Possibly for tungsten it's better. Do you plan to address this problem in any form, or at least what could you comment on how this, I would say, uncertainty, terrible uncertainty, of course, this goes not unlike the diffusivity, it's directly proportional to diffusivity, the flux to coolant. In terms of the recombination rate, it's the same situation as with incident flux. So basically it's under the square root proportionality in the steady state. But still, we're talking about the situation, then the flux of particles can be known 1 order of magnitude approximately from physics calculations, yes? But the recombination rate is basically 4, 5, even 6 orders of magnitude different under the same square root. So basically everything in those calculations of permeability of tritium to coolant is totally dependent on the quality of the recombination coefficient, not on the quality of the diffusivity or recombination on the water side. So recombination on the plasma facing side. What is the current state of the art, and what is, I would say, solution to make realistic estimation for realistic surfaces? For example, stainless steel surface facing plasma, not directly, a bit recessed, consequently bombarded only by neutral particles. Yes, this charge exchange reaction produce neutral particles. We need to understand what can be the recombination rate on this surface. What could be the approach to this?
Absolutely. So thank you for your questions. That's very interesting. Actually, I could have just done a 30-minute talk just about the surface, but it seemed to me that for master students, it might not be the most interesting approach. But you're absolutely right. We do have something very important happening on the surface. So I have someone on my team called Etienne Hody that has been publishing a lot on that and addressing those issues. And especially, so I'm right on the good slide. So that's that's nice. So I showed you this parametric fit. So we have codes at hand. So this is FESTIM, but we also work with Etienne's code, which is called MIMS. That was cross-checked with TMAP7. So it's quite robust and we know it works well. And what we do here is, so I purposefully did not address this here because this is all very nice and we have a good understanding of what's happening there. But there is a kind of a big discrepancy here and it's not that nice. And actually here, that's because the model I'm using does not include any surface effects. And that's not fully satisfying. Good news is we tried to use, and we managed using Etienne's code MIMS to actually simulate what's happening at the surface. What we do is we do not use recombination coefficients, but Etienne breaks down the surface processes at a finer level to understand the influence of all of those. And we were able to replicate this. So obviously, it's not for a sample that is as damaged as is going to happen in a tokamak, but we are not just using the usual Sievert's law to simulate what's happening here, but we are actually also using this TDS first to get the energies and density of traps, but also to get the energies of, for instance, adsorption and recombination of what's happening at the surface. So stay tuned. I am in the very last steps of writing a paper presenting those results. That should be out not too long.
Couple of additional yes, if it is possible. First of all, what was, I would say, kind of a goal in developing additional code for simulation with FESTIM, if in principle the same TMAP7 that you mentioned is available widely and for a long time and kind of standard, I would say, in the field. So probably your code can do some other things. And the question is, would it be possible to license it, for example, for ITER project? Yes.
So there we are slightly out of my pay range, should I say. So that's more to the developers. So actually here we are using FESTIM and that's, how to say it, it's very luxurious and it's not very needed for what I'm doing here. The most important thing about FESTIM is it's able to yield results in 3 dimensions, including interface work. So that's a huge work. What I do in permeation is always can always be restricted to just 1D. So FESTIM is much too nice for what I'm doing, but we still use it because it's easy to use and we have a Hemi on the team. Etienne, on the other hand, has been working on his own code because he's been simulating and trying to lace it with density function theory. So I guess that's also why he needed to have his own. But I might not know the whole reasons, the whole politics of having your own code versus using a different one.
So this code belongs to what organization?
These 2 codes are CA codes.
CA code, CA. So, and whom should I, for example, contact to discuss the possibility of licensing?
You should contact Christian Grisolia.
Excuse me, could you repeat once again? Etienne? Etienne or somebody else?
Here is his. I'm going to show you the names.
Yeah,
they are on the first
so
slide.
The name, yes, because it would be much easier for me.
So Christian Grisolia here is supervising all of us.
Okay.
And so those are the 2 authors of the 2 codes. So Remy did the Python finite element code that does 3D. Actually, he's already been doing some work with ITER. And Etienne did MIMS, which so both of the codes start to have quite a number of papers presenting them.
Okay, so probably I should contact Christian Grisolia.
Absolutely.
Yeah? Okay, thank you very much.
Thank you for a very interesting question. And yes, I don't see more hands raised, so I will ask one question myself. Maybe you will answer my question about the possible PhD positions in your team.
Yeah, so It's yeah, I mean, PhD positions, they come and go, and it's not just about my team. I mean, even I don't want to just do some advertising for my team. It was just also to maybe shine a light on the issues of PFCs, and that was just a very specific light on tritium retention and trapping. But there was also a ton of things to be done in just like the material science and how they handle temperature and recrystallization and all of that, because I feel like maybe this is not the most obvious field. When you think about fusion, you think about like the nice trajectories of particles in the plasma.
Yes.
But that's maybe a bit more on in the end of the line, so to say, but it's still a very important part of it.